So thanks so much, Rich and Raj and Nicola. So what I suggest that we do, Tim, is have all the panelists turn on their video, and so that because they'll be the visible folks to everybody, and everyone else turn off their video, which for those speakers. And with that, we'll turn it over to Tim Sherwood. I want to mention that Tim is a renowned computer architect at UCSB and an expert in a whole bunch of things in this interesting space. So Tim, with that, I'll let you go and take it away.
All right, thank you very much. Hope you can all hear me all right. Yeah, well, thank you for all joining us, and thank you for those amazing presentations. I certainly learned a lot, and I'm sure our audience did as well. So welcome everyone to who might be joining us now to the IE Emerging Technologies Review Workshop. This specific panel is here to talk about data center and cloud efficiency and sustainability and the future therein. And I think as we heard, there's a lot of exciting, interesting opportunities here for us to explore. And I think one of the things is this panel, it's a great thing for our community to discuss and understand sort of where you see the challenges and opportunities in this space. And I think one of the unique challenges, obviously, as researchers, is trying to go where the puck is going to be, right? Not where the puck is. And so how do we get there? Where should we be going? And what are the things that we need to be building and thinking about to help us get there? I just wanted to start with a couple housekeeping issues for everyone. I think the first is we have this Q&A widget, which I think people have been using well already. But if you have questions for the panelists, please go ahead and enter your questions in there, and we'll try to get to some of those. There's also a general chat widget. The chat is public, and so we encourage people to chat and stay engaged. And it's just a reminder to any of the non-panelists to try to keep your mic muted so we can hear our panelists when they are choosing to speak. So as I mentioned, I think this is a great opportunity for our community to really think about and hear your guidance on the opportunities and challenges in this space. And I should just mention for our panelists, that this is a really unique time for us. I mean, computing has really grown in leaps and bounds at UCSB, and over the past 5 years, I think you could make the case that this is the second most productive unit per capita. We have a lean and mean group here that do a lot of really high impact work, and I think it's a group that's ready to kind of make a positive impact. Is excited to kind of hear your thoughts on how we actually should be setting ourselves up to do that. And I think I also want to mention that the IEE is amazing resources. Has been an amazing resource in that journey, and the opening of the new experimental data center space is something that I'm hoping to discuss a little bit, because it kind of asks the questions, where the real opportunities are for us to be able to kind of use that space to have impact. With that, I want to introduce our amazing panel. It's such a delight to be able to introduce them. We already heard from Raj Yavatkar, who's the CTO at Juniper. Raj is responsible for charting Juniper's technology strategy. He leads and executes the company's critical innovations and products for intelligent self-driving networks, security, mobile edge cloud, network virtualization, packet optical integration, hybrid cloud. And you got to hear some of his wonderful thoughts already. Nicola Peill-Moelter is Director of Sustainability Innovation, and I think had a wonderful talk describing these zombies and what we can do about them, and really is a gosh, what a wonderful culmination of many of past experiences across the environment and computing, and bringing this all to have impact in industry here. I think it's amazing. We're also joined here by Brent Gorda, who's Senior Director for HPC Business for ARM. He's a technical business leader and entrepreneur. Is formerly the General Manager for Intel's High Performance Data Division, and all-round thought leader in HPC space, I will say. We're also joined by Mike Haney, who is the Program Director Emeritus at the Advanced Research Projects Agency Energy, better known, of course, as ARPA-E, where he led the development of programs in high efficiency solar energy conversion and photonic networks for data centers and high performance computing systems. And we're joined also by Jonathan Balkind, who joined UCSB as an assistant professor of computer science as of maybe a week ago, I think officially. And we're so excited to have him join here in this conversation. He was the lead architect of the Open Piton project, which is a heterogeneous ISA Open Piton project, and has also led heterogeneous ISA development with BYOC, which allows people to bring multiple different types of cores into the same SoC platform, and has built, Linux booting full machines from front to back and stood up real systems based on that. And I think he brings an exciting new set of capabilities here to UCSB. So I thought I would start. We already heard some wonderful presentations, but I thought maybe I would just start by calling on the people we haven't heard presentations from so far to maybe just kind of briefly say a few words about yourself and maybe sort of what you see as some of the challenges and opportunities regarding efficiency in the coming decade. And maybe I'll just go in order of introduction there. So maybe Brent, you could start us off if you would.
Hi, thanks, Tim. And thanks everyone for having me here. In ARM, our business model is focused on licensing IP, and generally the historical part of that is licensing IP on the edge in areas where performance is challenged by energy availability, so handhelds and mobile type devices. I represent the high performance computing piece of ARM, and high performance computing is recently spending a whole lot of mind share on efficiency in the data center. The goal 10 years ago was to try and fit an exascale in, I believe, 20 megawatts, and it's since been up to 40 megawatts. So we take devices and multiply them by millions to put them in one room and use them as a high performance supercomputer. The best example of that right now is a system in Japan called Fugaku, which is about 8 million ARM IP cores with SVE vectorization and high bandwidth memory. And so we spend a lot of time thinking about energy efficiency and movement of data. A lot of our researchers are looking at placing ALUs in the cache, for example, to avoid moving the data across the chip. The Fugaku machine I mentioned is HBM only. A node that's a little bit smaller than a piece of paper is 180 watts at 3 teraflops. So as part of that project and as part of most of the worldwide exascale projects, we're spending a lot of time thinking about what these designs look like, power management on these designs, that sort of thing. HPC's historically been a test bed for new technologies, which is the way we're looking at it, and expect that what we learn there will flow down back into the middle of the network. Already we think we do quite well at the edge, and my focus is right at the very high end and how we move that down into broader cloud and data center usage.
Great, thank you very much. Mike, maybe you could say a few words.
Thanks, Tim. Yeah, my perspective on data center and HPC efficiency is informed by a program we call Enlightened that we launched in 2017, which is based on the premise that integrated photonics-enabled networks would achieve better utilization of the compute resources if properly designed. In fact, we put a goal of a 2x improvement in transactions per joule. It's a very fuzzy metric, but it's something where we're continually refining. The other part of the premise is that this would drive us to co-packaged photonics to get to the picojoule per bit or less and tens or hundreds of terabits per second to the package of I/O for the high performance chips, switches, CPUs, GPUs, et cetera. The program, which you'll probably hear a lot about this afternoon, because there's a lot of people connected to Enlightened in the afternoon discussion, based on getting fatter and flatter fat tree networks based on photonics to get better utilization, or even using photonic switching itself to programmably get to different resources in the computing center. So we're launching phase 2 of Enlightened this year. Excited. I won't say a lot about it right now because there are many speakers that will address that. But I do want to mention sort of 2 general challenges that we find in Enlightened. One is pretty obvious, but it bears repeating that really it's a packaging problem. We talk about co-packaging, but it's become, I think, a packaging problem in the extreme for Enlightened. And it depends on which technologies you're using, whether it's silicon photonics or VCSELs. But they have common issues that are maybe somewhat different depending on the technology, fiber attach, what do the laminates look like. But we're trying to drive it to getting the packaging costs down, lower than the chip costs that are on the package, which is where electronics is. It's a daunting problem. And maybe as we go to scale, real scale, that will happen. The second key challenge I'll mention is a general challenge is a question is what workloads are we going to design to? We know what's happening with machine learning and AI. We know there's some bit of a convergence between data centers and HPC. How do we optimize our networks for energy efficiency to address future workloads, which are frankly a moving target? So that's my perspective.
Thank you so much. Jonathan, do you want to say something?
I also have a couple of areas that are of interest to me. The first of them, I started doing some research on function as a service or serverless computing. So this is kind of same area as microservices. And looking from an architect's perspective, we were interested in finding out about how is the architecture playing a role. And one of the interesting things was that FAST came about because the providers wanted to increase their utilization, right? They had, I think 2015, there was a statement from Amazon which suggested a 65% utilization of their servers, which is shockingly low if you're not somebody who's in that area. You're saying, okay, I could run 50% more compute on the resources that I have available. And so this kind of directly ties in with what Nicola was talking about, that we have these resources, they're not being well utilized. And the idea of FAST was to kind of better utilize these. So Rich's platform is one of these serverless platforms. But we're still using, people are wanting to write their code in languages like Python and in JavaScript, and they want to have a very kind of flexible environment. And so there's big questions, especially from the architects, the whole software, about how we actually run efficient code in these systems. In particular, if you bring something in and run a few iterations, and then you throw it away and you bring in something new, you've wasted a lot of kind of compute, a lot of data movement to be able to do that. And so that's one side. The other side is about with the end of Moore's law, if we're going to see our chips lasting for a lot longer in our data centers, if there's not a good argument to replace your hardware with something new, you're going to want to be able to really squeeze out your investment as far as possible. And so, I think this is a place where, we talked about kind of packaging issues. Actually, chiplets and the kind of architecture around the chip realm are going to be really interesting. If we have the potential to, for example, swap out chiplets, that would be a really kind of crazy advantage. Because you could swap out just the parts you wanted to swap out with new technologies. You could bring in whatever accelerators you want to bring in to give you the most efficiency, highest kind of compute density that you want to reach. And then the problem comes of how do you kind of plumb all these things together at the software level and make everything as efficient as possible.
Great, thank you. I kind of wanted to just pose a question to start to the whole panel here. I think Mike and Jonathan touched on this a little bit about what are, your thoughts on the hard problem, the things that, as academics, we have the ability to here to operate at different time scale. The time constants are slightly different. So, what are those hard problems that, should really be, we should be really engaging our students on and trying to kind of get people to rally behind to try to really address. You guys have any thoughts on that?
Yeah, I can certainly chime in. Sorry, Brent, did you want to go? Yeah, so I like to look at things at a systems level. And I think for even today, we tend to silo to hardware, to software, to networking. And I think we really need to look at the problem at a systems level because there's a lot of opportunity for intelligence and visibility across all of those layers for optimization. So Jonathan mentioned 65% utilization, I think. That to me is enormously high because what we see across our enterprise environments with our customers, and obviously we see across a lot, the utilization may be around 20, 25% if we're lucky, right? And so you can make a chip 1% more efficient, but is that any use if it's only barely being used, right? And then you have to buy, 100 more chips for your workloads. So I think there's a real opportunity in just even metricing to really understand across those environments what's going on. So it's from a utilization perspective and also productive utilization, right? That's a very hard thing to define, and it's almost in the eye of the beholder. So can we get to, say, benchmarks where we can compare, is your environment being productively used? Because at the end of the day, energy and carbon come down to, are you maximizing the workload productivity of the IT infrastructure? Because if you're not, that means you just need more IT infrastructure and more data center space and more energy and more carbon. So ultimately, it really comes down to, as Jonathan was mentioning, even at the code level, are we, we hear now there's, just because VMware has Spring Boot, right? That's the Java development platform. And the plugin that is the Graal VM, which is taking Java code and converting it into assembly code. And it runs more efficiently. Now, it's not always ideal, depending on how often that application runs, et cetera. So you have to optimize. So there's, in my mind, there's all kinds of opportunity, but we have to, again, see it at a systems level and get those metrics and get the analytics and see where the opportunity lies.
An interesting panel always requires a debate. So I'm going to completely disagree with you for the following reasons. I worked at both VMware and Google. I don't think the system level co-optimization yields much. The reason we have a code bloat, to Jonathan's point, is because we have Spring framework, right? Spring is the worst thing that happened to programming, in my opinion, or Java programming, because it creates a code bloat. One of the things that Jonathan mentioned, I want to comment on, 65% utilization hyperscalers getting. I worked at Google, I can tell you. Google routinely gets that. Why? It's not because they're doing system level co-optimization. It's because the how you schedule and make sure the VMs or tasks that are not doing anything useful, you don't have to schedule them. They should not be using in memory. They should not be using any CPU. You put them aside. So I think the problem in enterprise computing has been that a lot of the good things that are happening in hyperscalers are not trickling down. Because enterprises are served by vendors, it's in their interest to have an efficiency because that's how you sell more equipment. That's how you sell more software. One question I have for Jonathan is that you mentioned the coding, Python, JavaScript, or even Java Spring. There's a new movement called really no code or low code movement. Do you think that is a way to go so that you can take it away from the programmer and somewhere else you can optimize for power efficiency?
Yeah, I think there's going to be a big outbreak of this kind of thing when people see that what they're running in their serverless environment isn't any different to what somebody else is running. But if they can ever see that, there's a lot of kind of vendor lock-in and so on. But like, if you're just running something to munch some data that came out of a database, why do you need your code to do that? Can somebody else's code do as good a thing? Can the provider provide a shared service that everybody uses instead? And gain an efficiency across their kind of disparate customers who have different needs. So I definitely think, and that will work mainly for this kind of more kind of public environment where you have a disparate set of users.
Brent, I know you wanted to hop in there earlier. Do you want to?
Yeah, I was going to agree on the systems level. One of the things I've learned since joining ARM is that the power consumption of a CPU is shockingly low, like half a watt for a single CPU. And so I think the big win in the near term, sorry, I'm going to have a cattail in my screen here. The big win in the near term is at the systems level. We can optimize the heck out of the socket, but the rest of the system still takes up a huge amount of it. I was sitting here trying to look up, we belong to a consortium at Lawrence Livermore National Laboratory that's looking into these sorts of issues. And my sense is there's a lot of low-hanging fruit to be had by dynamically controlling the power to idle resources. And in my environment, with 8 million CPUs and 1 million GPUs, they're not all flat out at the same time. If you can dynamically switch the power and do so in low latency, you could probably save a huge amount of energy. one of the things I learned at LINPACK at Livermore is that when we would run LINPACK, we would hit the peak power consumption of the data center. We would only run that the first week we had the machine. We would never run that application again. And so we were way over provisioning the data center for the silliness of running the top 500 benchmark.
So Brent, I want to clarify my comment, right? I think I completely agree with you. For each of the resources, there's a huge opportunity for optimization. I was commenting on the co-optimization aspect, which gets oversold sometimes because having done systems for many years, I think I'll give an example. You gave an example of LINPACK based over provisioning. Somebody asked a question in the panel. The telecom vendors in Europe found that when after COVID, the amount of data traffic went up, energy usage did not go. Why? Because they have built overcapacity. They always buy routers so that, which is good for Juniper's business. I'm not complaining, but I think it's not good for the environment because if you put too much capacity, of course, you can easily take up 40% more traffic. But none of the requests for proposals or information require equipment vendor to say, you must achieve so much energy efficiency. Right? In the switch fabric and all, there are lots of parts which are not being used. You can optimize them when you're not being reduced to power. But that sort of focus would help a lot, in my opinion, in each of the resources by learning from each other's mechanisms than trying to find sources of co-optimization first.
A comment that's somewhat related. One of the exciting developments in the Enlighten program is several of the teams are looking at photonic switching to dynamically alter the network depending on the workload specifically, and change it, in a sub-second time frame if needed. And some of the early emulations of this have proven that it can be very effective at resource utilization, even with relatively slow photonic switching, but massive amount of bandwidth to connect memory as needed. It's essentially a hyper disaggregated approach, I think, that has some payoff in terms of resource utilization.
So it was a great discussion. I mean, this is what you hope for with a panel, some good back and forth. And, one of the things I just heard sort of as a thread through all of this, I mean, Mike, you started talking about workloads and the workload choices being one of the challenges. And I know, Nicola, you mentioned, utilization, but also what is a benchmark and a metric you use here? What is an appropriate way to characterize these things? I'm hearing some questions about the theme of what are these computing workloads going to be in the future, and how do we measure them? And I'm curious if you have any thoughts on that, where you see those workloads going.
Yeah, well, I think as sort of Jonathan was saying, it's becoming more diffuse, right? Before you have monolithic applications that were all in Fortran or COBOL, right? Running on a physical server. And now it was virtual machines, and then it's containers, and it's functions, and it's microservices, and it's serverless, and it's in cloud, and it's on-prem. And so I think the idea is, it's almost like it's a fractal, right? So you're going to smaller and smaller pieces. And I feel like there needs to be an awareness, a self-awareness of that, whatever that code is, about, am I being productively used? and not only that, but of course, that's just one application that could be running on a physical server that's doing a lot of things. And for example, if it were doing no productive work, it could still be going out and doing a patches update, right? Or some kind of checks and balances that was sort of a background thing that's not really valuable unless you have applications running on it. So I feel like every application, no matter what it's doing, has to have some self-awareness about productivity, maybe about energy, maybe about carbon, but certainly about doing something productive.
Well, one of the, I don't have a specific answer, Tim, to your question, because it's a very hard question. So in Enlighten Phase 2, we're actually standing up a working group with members from all the projects to address this workload question. In fact, we'll be inviting people from outside, but potentially people from this very panel to help us have this workload discussion as an ongoing piece of the program to optimize how we go forward in designing these networks based on photonics. So it's a key question that will take a lot of study I don't think we'll answer it today, but it's good to have some directions to help us.
The only comment I would make is that making the workload self-aware for self-optimizing is much harder because you require raising the bar for programmers, right? And today we are getting programmers who start programming in high school. So the first thing they learn is unfortunately JavaScript or Python. Now getting them to go like is much harder. I would rather move more to removing the program because programming is really becoming like a role of electrician or plumber. A lot of programming, right? Not all of it, unless you're developing new algorithms like machine learning and implementing them. So removing the requirement that you even have to program, that's what the no code movement is a much more promising direction in my opinion.
I apologize if I keep dropping off here. I'm called in, so I can still hear you and participate in the conversation if my video drops off here. So ironic in such a networking focused panel that I'm having network problems here. But if there's any other comments on that? Yeah.
Yeah, I just wonder how much AI and ML can help here in the sense that, because you don't really want to use more energy with the AI and ML than you're saving potentially. But I'm wondering, for example, if there's kind of a watcher that says, okay, what's the initial activity of this application? Of course, application, again, could be across many different environments and different modularity. But because I feel like if this application is doing something initially, right, presumably that's what it's meant to do, and then dramatically changes over time, usually to either almost no activity or to very, very high activity in kind of a rogue sense. Is there a role for AI and ML here? So maybe we don't have to put it in the programming language. Maybe it's more of a watcher.
So I can give an example of data center if you want, right? In a data center, there's a huge opportunity to apply ML AI. DeepMind, which is a Google company, they did this for Google's data centers. They applied machine learning and AI. But because one of the things they found is that the configuration space for a data center is huge, right? You have so many components that you're configuring. And each one of them has alternatives. So the search space for optimal place is very high, very complex. So by applying DeepMind's algorithms, now it's a published paper, you can look it up. They showed that they can improve the data center efficiency by 30% or something like that. It's a big number. And basically, because configurations are so many, optimizing those configurations cannot be done by human beings. So they applied a machine learning model. That could be one example of that.
So we have an example from we have an example from the labs. A guy named Rick Stevens, who's the director at Argonne National Labs, talks about using AI to steer computational progress, specifically with respect to cancer research. We used to talk about computational steering in the 90s, where a human would look at the data as the application was going along and suggest where the interesting bits might be. That's kind of progressed to where the AI is now looking at the data and suggesting where the application might find good results to go steer. That sounds really promising.
Great. John, let me know if you want to hop in if you have a question here. I saw you enter.
Sure. Well, there was a question earlier that went to Raj, and there's something Mike Haney knows a lot about, so I thought maybe I'd direct it to him. But the question earlier on was, contrast silicon photonics versus VCSELs. And my twist would be particularly in the case that Raj was talking about. As we go forward, he indicated at 1.6 terabits that coherent was more, power efficient than direct detection. So maybe just what's your viewpoint on those issues? Because I know you're funding coherent and VCSELs and silicon photonics.
Yeah, sure. As John said, we under Enlightened, we do have a major VCSEL project and several silicon photonic projects. And for those of you not aware, VCSELs versus silicon photonics has been a more or less healthy debate for decades in terms of the interconnect world. My view is that, well, certainly fundamentally, silicon photonics with wavelength division multiplexing is fundamentally more dense in terms of bandwidth to the chip, and has more leg room for future advances in this direction. VCSELs, of course, have been very successful and may address the nearer term opportunities, especially if they can address the packaging and cost issues sooner. But I think the long future will be silicon photonics, and but we do have a team, IBM and Finisar, on pushing very, very hard on getting everything out of VCSELs we can, and they have quite different packaging challenges, as you might imagine, maybe different application domains as well. So that kind of wraps up my view at this point.
It seems inconceivable to me that at the stage we're talking about for data centers, like a 51 terabit switch, that you could put enough multimode fibers in that package to transmit the data. So to me, there's only one answer. But again, particularly for 1 terabits, what's your thought?
Yeah. So yeah, I think again with maybe some signaling and maybe coarse WDM, you can push VCSELs a bit farther to whether that limit is 50 terabits to the package or 100. I think is an open question. But there's definitely a wall there, fundamentally between direct modulation VCSELs and wavelength division multiplexing silicon photonics.
I wanted to, we have maybe about 10, a little less than 10 minutes. I wanted to, one of the things that's really interesting, I think, about IEE is this new experimental data center space that we're standing up as the opening of the new building that both John and Rod talked about. And I was curious to think, I think it's a real opportunity for us as a campus to sort of, do some research. It's a research capability that I don't think is available to many of our peer institutions. And, it's an opportunity for us to kind of do some stuff that others might not be able to. And I'd be curious to hear your thoughts on, sort of as academics, research at scale that we might be enabled there that you'd be excited to kind of see start to happen. Or other thoughts on how we might utilize that space to greatest effect.
Well, I can mention one thing that VMware is doing. It's definitely a skunkworks project, which is to use VMware's capability to move workloads around, and that could be within a data center, it could be from a data center to the cloud or off-prem somewhere else. And I think Google's doing this, right? Is they're trying to match when the renewable energy is available to power the workloads, and when it's not, they would move the workloads around. But one of the things we're experimenting with is, can you move the workloads inside a data center so that you can optimize the cooling? So for example, concentrate workloads in, say, one area of the data center and just have the cooling in that area when maybe the workloads are low, or you have your critical workloads where it's very cold, and then you move your less critical workloads to areas where you don't have to cool it as aggressively. Or I think it just depends also on the hardware too, right? Because a lot of hardware can withstand higher temperatures. But the idea is to kind of optimize based on moving the workloads around rather than moving the servers around or the cooling around.
Thank you. Anyone else want to hop in there? Oh, you're muted.
I'm very curious to see where the edge computing and Internet of Things in general goes. I think that I can't even define the problem yet, but I think there's a lot of work to be done to get to high efficiency use at the edge. And what do those systems look like? I've heard terms like near edge and far edge today, and how does that all come together, and where are the efficiency challenges and opportunities? I think that's going to be right for the academic community.
And I think pulling on Rich's talk a little bit, I think the data movement problem is a big opportunity here, right? Having an ability to optimize how much data you actually have to push one way or the other, I think you would find that would be converted easily into energy savings. You could solve that in a generic way. Sorry, Raj, go ahead.
No, sorry, I agree with you. Combining data and computing as close to where it is needed rather than migrating data, I think is still an open question. I like Rich's talk a lot because what they're doing with Spot is pretty much spot on. I think it could be evolved. Yeah.
No pun intended.
No problem.
Oh, that's great. You know, one thing that I also heard as sort of a little bit of a theme through some of the discussion here was this: there's a productivity and efficiency sometimes might be related or potentially in conflict, right? And you talk about the role of languages and no code versus Python. I mean, dynamic languages, do come with a lot of overhead of efficiency, but there's a reason they're so popular. I don't think it's simply just because it was their default choice. That seems like an interesting challenge. I'm curious if you have any thoughts on, when those two things are in conflict and when we can kind of work them together.
Well, I had mentioned it's sort of a plugin that I guess Oracle had developed. It was open source called Graal VM. And the idea of it is to convert higher, in this case, Java, right? But you could say object-oriented programming into assembly code, which obviously runs more efficiently and instantaneously. And so I do think that might be, it's very nascent, and there's probably lots of issues with it and challenges. But I think that might be a pathway forward, right? Is if we could code in these higher level languages, and then that gets compiled into assembly code, that might be a sort of a happy medium.
Yeah, I think this space is really interesting because I remember maybe, I don't know, 8-10 years ago, talking to a friend of mine who was doing web development, building web apps. And he was telling us about how, oh yeah, I would have coded this way a couple of months ago, but then I read that actually if I change it to this other thing, then the JIT compiler in the browser is, way more efficient at running that code instead. And there really wasn't any feedback to tell him this other than he stumbled upon somebody's Stack Overflow question that said, I hit this and it was too slow. But I think that programmers are more responsive than we think when it makes sense for them, when they want to get the performance back or get the energy, kind of maybe not energy efficiency, but some sort of efficiency back. And so I'm kind of interested in what ways we can feed to the programmer to say to them, hey, you could be doing this better, right? And I think one of the interesting places that this has really been taken up is the domain-specific languages, like, we've got PyTorch and TensorFlow that are really heavily used for machine learning, and people are coding that in Python, right? Somebody's built some language inside of Python to provide this capability. So, I think trying to investigate in this space continues to be really interesting.
And what about training students in schools to think about efficient coding and efficient architecting, as opposed to, it's kind of like green chemistry, right? It's maybe let's invent new chemicals without using toxins. That might be a good idea. To code efficiently the way we do for iPhones and mobile phones.
But I think the computer science education in my opinion has struggled with this for a long time, right? We had Pascal to Scala to Prolog. I mean, different. I'm of course telling you my age or experience, I think, in this case. And people have, I think it's very hard to get programmers to be very aware of. I mean, there are programs, embedded programs, people who do kernel programming, people who do embedded, they're extremely good at squeezing every cycle out of the code. But that's a very small fraction of the population. I think getting the larger population to do that is much harder. Unless, to Jonathan's point, you add some language constructs to give hints, like pragmats in the code. Oh, this part of the code can be made a lot more energy efficient, but you have to use more automated tools to do that, in my opinion. But expecting the programmers to, en masse, learn efficient coding, I'm very skeptical.
Yes, John.
I had a question for Raj. So, I mean, you talked about the 51 terabit and having to get rid of 1.6 kilowatts of power out of that co-packaged chip. That sounds like a real challenge. But my question is a little further out. What's at 102 terabits? What happens then? Now you're only spending 500 watts on the optics, which I wish that were a bigger part of the problem. But what do you see for the next generation beyond 51?
Yeah, I know that's a very open question, and that's where I think somebody like DARPA and ARPA need to do a lot more investing in my opinion, because the new technologies will be developed to address that. But it's not path clear. But I think hyperscalers are going to push very heavily. They're starting the internal programs to look beyond 51.2. At least I know of two efforts in two hyperscalers. They're doing that, and they basically going back to basics by hiring these physicists who are looking at very different ways of transmitting data. Right? I think there's going to be a combination of things that will come. My only concern tends to be that technologies developed in hyperscalers don't necessarily trickle down to the outside world. So having original model of DARPA taking big challenges on and funding would help accelerate this kind of work. That's something I believe, since Mike is here, I was bringing it up because, that's something that we do lack in the country right now compared to what it was 30 years back or 20 years back.
I appreciate the message and we'll take it forward.
A naive question, Raj. At 1.6 kilowatts, that must be water cooled, isn't it? You can't air cool at that rate, can you?
Yeah, or chilled air or a combination of that plus, yeah. It's very highly concentrated, I think. So some new cooling mechanisms, a combination of the cooling is what people are looking at. By the way, that's another area which continued innovation is possible. There's going to be lots of innovation in that space.
Well, I think John has provided a transition here to the second half of the day, where we're going to talk a lot about. There'll be plenty of time to talk about all manner of silicon photonics here. But I really want to just take a little bit of a moment to thank our panelists here for the thought-provoking discussion. I think you gave our community here a lot to consider. I encourage you to stick around for the rest of the day if you can. And William's talk at the end, I think, will also shed some light on some interesting discussion around workload and sort of problems that are driving energy efficiency issues that of human importance. So I hope you'll consider sticking around for that. And with that, I just want to thank everyone, panelists again, and for the audience for their attention and appreciative questions. Thank you so much. I'll turn it over to you, Mark.
Yeah, thank you so much, everybody. Rich, I wanted to ask if you had any concluding comments for the overall session. But that was a wonderful panel. That was great. Raj, thank you so much. Mike, Nicola, Jonathan, and Tim for chairing. Brent, I mean, it was great stuff. So
yeah, and I want to thank everybody. Sorry, my camera ceased to work after I stopped sharing my screen. I don't know why, but I just wanted to say thanks, and also to point out, how diverse the discussion of energy efficiency has become. So when I started thinking about these problems several years ago, there was this segment of the community that was focused on what we could do at the hardware level, and then there was a segment of the community that was focused on what we could do with respect to workload migration, as we talked about. Now, I mean, just if I look back on the last hour and a half, I think, wow, it's such a diverse area. It's so multidisciplinary now. That to me is really encouraging. I think that's how innovation happens, when we start looking at these problems, in much broader context. And so I just want to thank everybody for their commentary and for their sharp thinking on this area.
Yep. Thanks, Rich.
Thank you.
Thanks, everyone.
yeah, okay. Thanks, Rich. And John, I wanted to reintroduce John Bowers, who's going to chair and moderate the next session. John is chair professor at UCSB and is absolutely, National Inventors Hall of Fame, and is the director of our institute, and again, one of the real pioneers of silicon photonics. And the rest of the day, and John, when you have a chance, if you want to put up the agenda for the rest of the day, that would be great. I can put it up if you prefer. But John will be chairing the remainder of the day up until William's talk, so for the next few hours. And thank you all to the morning session. It was a great session, climaxing that wonderful panel. So thank you. And John, I'll hand it over to you now.